Okay. Good afternoon. It's an honor to be here and make this presentation. The topic of my speech is electrochemical conditions optimization and techno-economic analysis on the direct CO2 electron reduction for fuel gas. The speech will be developed into 4 parts: the background, model and methods, results and discussion, and conclusions. Compared with the vigorous development of industrial technology, the absence of carbon reduction technology leads to an unbalanced carbon cycle. Climate change and energy deficiency caused by the unbalanced carbon cycle are global problems. Efficient and budget carbon reduction technology is urgently needed. Due to the need for carbon reduction technology, the research field of electrochemical CO2 reductions has rapidly developed in recent years. As shown in the table, the carbon dioxide can be electrolyzed to C1 and C2 products and so on. This technology has the advantages of mild reaction conditions, controlled process, and faces the challenges of slow reaction rate, low efficiency, and high cost. The majority of studies focus on the catalytic properties on the pure CO2. However, the cost of CO2 capture and purification is nearly 10 to 30% of the overall system cost. Direct CO2 electron reductions for fuel gas can reduce costs and simplify systems. Typical fuel gas is composed of nitrogen, carbon dioxide, oxygen, and trace amount of oxysulfide and oxynitride. The challenges of low CO2 concentration, competitions of oxygen reduction reactions, and the interference of oxysulfide and oxynitride led to the low efficiency and low rate of direct CO2 for fuel gas. The present work studied the characteristic of fuel gas electron reductions, effects of electrochemical conditions, and their industrial potential evolution. The second part is model and methods. Based on the experiment structure, a 2D cathode reaction models is developed. The models consist of 4 domains: electrolyte, catalyst line, GDL, and gas flow channel. The CL is a weighted porous media with electrolyte, catalyst, and gas. The GDL is generally a fibrous media, which plays a role in supporting the CL, collecting the current and conducting the gas. During the cell operation, the fuel gas passes through the gas flow channel and the GDL, dissolving in the electrolyte of CL. All product generation reactions are considered based on the catalyst. HER, OR, CO2R are occurred on alkaline process. And the homogeneous reactions for dissolved fuel gas are also considered. The conservations of potential, momentum, mass, space, and energies are applied to describe the characteristic of fuel gas electron reduction. And the components of fuel gas boundary conditions are shown in the table. The governing equations are solved by COMSOL, a structure squared grid with appropriate refinement at concentration boundary layer was used. Current density and Faraday efficiencies are 2 indicators of cell performance. Current density reflects the rate of an electrochemical reactions, and the Faraday efficiencies reflects the selectivity of products. pH, temperature, dissolved CO2 concentrations are the indicators of electrochemical environment. The results of the present models are compared with the experiment for validation. The simulated results has good agreements with the experiment. After validation, the product distribution of fuel gas reductions is compared with pure carbon dioxide reductions. The variation of reaction gas components greatly affects the selectivity of the product. The selectivity of CO2R decreased from 56% to 5.5% at high temperature. The changes in product distribution result from the electrochemical environment. The average dissolved CO2 concentration, current density, temperature, and pH in CL are compared. The solid line represents pure CO2 and the dashed line represents fuel gas. As shown in the figure, direct CO2R for fuel gas face an extremely severe electrochemical environment with weak CO2 concentrations and unstable pH. To solve the problems of low efficiency for direct fuel gas reductions, pressurization is proposed to increase the CO2 supply. With the increasing pressure from 1 to 20 atm, the total current density increases from 200 to 300. And the selectivity of CO2R increases from 1 to 47%. Compared with the dissolved CO2 concentrations for 1 to 20 atm, the pressurization increases the dissolved CO2 concentration and maintain a uniform concentration distribution in CL. Moreover, pressurization enhances the stability of pH in the cell. However, pressurization causes the localized high temperature inside the cell. The maximum temperature of the cell increased from 320 to 340 Kelvin. The increase in neutralization reactions of SO2 with pressure is the main reasons for the temperature rise. The effect of electrolyte inlet temperature on current densities is studied. The increasing temperature promotes the total current density and HER. However, increasing temperature reduces the solubility of oxygen and carbon dioxide, so inhibiting the corresponding reactions. For every 10 Kelvin increase, the current density of CO2R decreased by about 7%, while the current density of HER increased by about 15%. By controlling the electrolyte inlet temperature for the enhancement of CO2R reactions and suppression of HER can be achieved. Further, to demonstrate the industrial potentials of direct fuel gas reductions, this section compares the full life cycles cost and profit of two options: purified CO2 electrolysis systems and direct fuel gas CO2 electrolysis systems. In these systems, the fuel gas is pressurization to 20 atm and then fed to the electrolyzer without purification. Moreover, the electrolyte is cooled before feeding. For both planes, the CO2 dissipation rate is assumed to 100 tons per day. The lifetime is 20 years, and the design parameters of CO2 electrolyzers are based on the above simulation. Due to high selectivity of CO2, the power requirement of fuel gas electrolyzers is lower than that of purified CO2. And because of the complex systems, purified CO2 systems need more $6 million for capital cost and operating cost. The net present value is used to assess the time value of revenues for the two options. The cumulative present values of fuel gas takes 2 years to achieve a turnaround, while purified CO2 electrolyzers takes 5 years. The NPV of fuel gas is $70 million, which is 2.5 times than purified CO2. With simplified systems, low cost, and superior electro reduction performance, the direct CO2 reductions for fuel gas has great industrial potential. In this work, 2D models considering fuel gas component effect, fuel production generation reactions is developed. The electrolyzers is dominated by HER with weak CO2R when fuel gas is the reaction gas. Pressurization effectively improved the electrochemical environment. Low inlet temperature can effectively inhibit HER. Direct CO2 reduction systems for fuel gas with pressurization and temperature control is 2.5 temperature times more profitable than purified CO2 reduction systems. Okay, that is the end of the presentation. Thank you.
Okay, thank you very much. Can you hear me?
Yeah.
Yes. Okay, good. So is a fuel gas or flue gas? Can you clarify it?
Flue gas, sorry.
Flue gas, yes, yeah, okay, that's good.
Yeah.
That's good. That's what I thought. Okay, excellent. So thanks for your presentation. And you didn't really introduce yourself. So I saw from the first page, you're from Jiao Tong University. Are you doing
Jiao Tong
PhD?
University.
Yes. So what do you do there? Are you a PhD student?
Oh, I'm a PhD.
Okay. Well done. I'm very impressed by the progress you're making. So which year are you in now?
4 years.
Okay. So then what's the for this project, what's the next step you would suggest? What do you see as the next steps for your project?
Oh, okay. I will do the experiment to validate the idea of the idea of the presentation. I
think that's very good direction. Do you have any industrial partners you can carry out your experiment?
Sorry, I don't have the.
Okay, that's fine. Yeah. Okay. Good luck with your PhD life.